Hey everyone, welcome to The Explainer. Today, we're going to gently unpack the unseen forces that are, quite literally, powering our world. Look, if you're a college student staring down a textbook full of intense electrical engineering formulas right now, just take a deep breath, okay? We're going to step away from that academic anxiety and move toward a place of clear, intuitive understanding. We're breaking down the analysis of single-phase AC circuits consisting of a simple resistor, and we're going to do it by focusing on the harmony behind the math. So, let's dive right in. I want you to start by thinking about something incredibly mundane, like have you ever stood in your kitchen waiting for breakfast and just listened to the gentle hum of a toaster? Or maybe you've been sitting at your desk late at night, perfectly focused under the warm, steady glow of a reading lamp? We totally take these things for granted, right? But what you're actually witnessing in those quiet moments is this invisible, rhythmic transfer of energy. It's not magic. It's actually a perfectly choreographed physical process happening right inside the wires.
Section 1. The Rhythm of Electricity.
To really get this process, we first need to rethink how energy actually travels. So we need to talk about alternating current, or AC. Now I know textbooks often present AC as this intimidating math problem, absolutely packed with integrals, but just look at how it's visualized here. While direct current is just a flat line, alternating current is this beautiful sinusoidal wave. It's cyclic. The current flows in a positive direction for half the cycle, and then smoothly, naturally reverses. Think of it less like water just rushing in one single direction, and honestly more like the rhythmic push and pull of the ocean tide. Or, a steady breath.
The main thing to remember here is that it is not chaos. It's a continuous, completely predictable pulse. When you see those complex cosine functions in your source material, like the equation expressing instantaneous current as a function of time and frequency, man, it's so easy to feel overwhelmed. But I really want to reassure you here. Those equations, they're simply the language we use to describe the steady, predictable electrical heartbeat. It's literally just math trying its absolute best to draw that smooth wave. Section 2. Meet the resistor. So, now that we have our rhythmic energy, we need to introduce the environment it travels through, specifically the absolute most straightforward component it will ever encounter. And that is the humble resistor. By definition, a resistor is a passive element. And all that really means is it doesn't supply energy to the circuit, and unlike some other components you'll study later, it doesn't store energy either. Its one and only job is to simply dissipate energy. It takes that rhythmic electrical wave and transforms it directly into something else, usually heat, like in our toaster, or light, like in our lamp. It's basically the uncomplicated, honest path in our circuit.
And this brilliantly illustrates just how uncomplicated it really is. This quick handwritten note outlines Ohm's Law, showing that at a constant temperature, the current passing through a conductor is directly proportional to the voltage across it, V equals I times R. The resistance is literally just a constant multiplier. A resistor doesn't delay the current, it doesn't fight it, and it definitely doesn't hold anything back. It just takes the voltage and translates it directly into current through this beautiful, constant, linear relationship.
Section 3. A perfect harmony.
All right, so we understand the AC wave, and we understand the simple resistor. So, what exactly happens when our rhythmic AC pushing force actually meets this beautifully simple, unchanging resistor? Well, to put it simply, they dance. Voltage provides the rhythmic push of energy, the pressure, and current is the actual flow of the electric charge responding to that push. Because the resistor is completely passive and doesn't store any of this energy to release later on, it doesn't introduce any delays. The current responds to the voltage instantaneously. They move together in an identical, perfectly synchronized motion. And that brings us to a really crucial point, the in-phase relationship. When a single-phase AC circuit contains only a resistor, the voltage wave and the current wave are entirely in phase. Notice how they rise together. They reach their maximum peak at the exact same time. They fall together, and they cross that zero line in perfect unison before reversing direction. Seriously, there is zero lag, there's no delay, and absolutely no complication. It is a completely harmonious transfer of energy.
Section 4. Finding the balance. Now this does lead us to a pretty practical question. If the energy is constantly rising, falling, and waving back and forth across zero, how do we actually calculate the heat coming out of that toaster? Look, I know this page on steady-state analysis seems intense. It's packed with integrals and peak factors. But gently guide your eyes away from the dense formulas for a second and focus on the core concept at play here, the root mean square, or RMS. Because an alternating current's true average over a full cycle is mathematically zero, since the positive half completely cancels out the negative half, we need a clever way to find a meaningful average for the power that's actually being delivered.
And that mathematical journey gives us the form factor, which for a sinusoidal wave is exactly 1.11. This number is just a simple constant born from dividing the RMS value by the average of a half cycle. You absolutely do not need to stress over deriving it every single time. It exists just to act as a bridge. It's a mathematical tool that helps us step from the reality of an undulating, changing wave into a functional, steady value that we can actually use in real-world engineering.
Because ultimately, RMS is just finding the balance point. Think of it as finding the steady DC equivalent of our rhythmic AC wave. It's essentially a way to calculate the real effective power that our resistor is dissipating by treating the wildly waving current as if it were just a flat, steady, predictable line of direct current. It allows us to apply really simple, steady-state logic to a dynamic, alternating system. Pretty clever, right?
Section 5. A peaceful takeaway. We've gone all the way from the raw concept of an alternating wave to the mathematics of steady-state analysis, but I really want to bring this to a calm, grounded conclusion. Check out this quote taken directly from the text we just reviewed. An alternating current will deliver to a resistance the same power as a direct current of value equal to the RMS value. This single sentence proves that at the end of the day, all that complex integration, all those wild sine and cosine functions, they just bring us right back to a simple, balanced energy transfer. An AC wave pushing through a resistor does the exact same amount of real, tangible work as a steady DC battery of the equivalent RMS voltage.
So, the next time you open up your basic electrical engineering textbook and feel that sudden wave of panic at the sight of sine waves and phase angles, just remember this. You don't need to memorize the chaos, you just need to understand the harmony. Because beneath all those dense formulas, electrical engineering is really simply about finding nature's balance. It's just a wave, pushing and pulling through a wire, perfectly in sync, heating your morning toast. Which makes you wonder, what other invisible everyday harmonies are hiding right in front of us, just waiting to be understood?